So our last plenary is by my friend Jacopo Buongiorno, and he is the Tokyo Electric Power Company professor and associate department head in the nuclear science engineering department at MIT. His expertise in thermal fluids engineering and reactor engineering. He is the director of the Center for Advanced Energy Systems, CANES, which is one of the 8 low-carbon energy centers at MIT energy initiative. So here I would actually like to acknowledge the support of MIT, who have a desk outside. They've done a lot of organizational work, even though they're not directly sponsoring this conference. And Jacopo is also the author of the most recent MIT study on the future of nuclear energy in a carbon-constrained world. So,
all right, thank you. I hope you guys can hear me fine. Do I still have 40 minutes, or? Yes. Okay. Anybody collapse yet? No? Can you survive another 40 minutes before we go to lunch? All right. Great, so thanks, Drew, for the introduction. So as Drew said, I'm going to leverage the results from a recent study on the future of nuclear energy in a carbon-constrained world, which I directed along with other faculty and students here at MIT. We chose the words carefully. It's energy, not just electricity. Nuclear energy can be used for a variety of energy products, as I will explain. And the focus of the study was not only the United States, it was the world, one in which people care about constraining carbon in the atmosphere, okay? However, you will see that this presentation that I put together for you guys today is somewhat more US-centered, and I'll point out where the US differs from other countries when it comes to nuclear. Now, in keeping with Dan's upbeat tone, I titled this Nuclear Energy, A New Beginning, but I couldn't help putting a question mark at the end. It's certainly nuclear faces challenges in the US and elsewhere. So let's see if this works. Great. So a good practice in giving presentation is to give the important messages up front. Then you guys can sort of sleep for the rest of the presentation. At the end, I'm going to snap my fingers and say conclusions. And you say, wow, now I need to pay attention again. So you'll see this slide twice, now and at the end. So there are, what we found is that there are basic features of nuclear energy. For example, it's high energy density, the fact that it's dispatchable. You generate, for example, electricity when you want it. You're not at the mercy of intermittency or Mother Nature. It has no emissions. The fuel that we use, which is uranium, is practically unlimited. These features remain relevant and attractive today to the US and the world. These are features that have been known since the dawn of the nuclear age 70 years ago. We also, however, find that the current DD&D, which stands for Development, Demonstration, and Deployment paradigm for new nuclear power plants, is expensive, inefficient, and particularly in the United States, there are ways to reduce the cost and schedule, the time it takes to put new nuclear capacity online. And so we'll discuss that a little bit. There are also some reactor technology innovations that could open up new markets for nuclear. This is this business of power and electricity is not the whole picture. If you look at the total amount of emissions in a place like the United States, about 1/4 to 1/3 is associated with the power sector, but vast majority is associated with other sectors, industry, transportation, agriculture, and so on. And in those sectors, nuclear can help as well. And finally, here you'll hear messages not just for the nuclear industry, which has been incredibly inefficient at building new nuclear power plants. They have to pull their act together, but the government also can and should help in turning the situation around for nuclear and therefore helping with decarbonization. So let me jump in. What is the value proposition of nuclear? Now, here at MIT, we don't get a paycheck at the end of the month if we don't show you some equations in every presentation. This is very simple chem with respect to what Dan has just tortured you with. So fuel energy content. So nuclear plants emit no CO2 or other criteria pollutants and do not require continuous fuel supply. How does that happen? Well, if you're a coal-fired plant, well, you're using combustion of coal, so the reaction is shown there. And let's say that you produce or you liberate 1 unit of energy. If you do this with natural gas, it's a similar combustion reaction. So you get your energy out, some CO2, which is bad news, a little bit more energy, 2 units of energy, okay? So when you actually transition from coal to natural gas for the same amount of electricity generated is good news in terms of CO2 emissions because it's roughly half. But with nuclear is a real game changer because here you're not breaking bonds at the atomic level, you're breaking them at the nuclear level. And the forces that hold the nucleons together in the nucleus are much, much stronger. So when you break those bonds, there is a lot more energy that comes out. How much? So the reaction here is not a chemical reaction, it's a nuclear reaction. You have a nucleus of uranium-235, the isotope 235 of the element uranium. It splits into 2 halves. In this case, it's shown as rubidium and cesium. Throws out a bunch of neutrons, which are important because you create a so-called chain reaction that gets the thing going. But what's most important is the last number in that line, that is 50 million units of energy. So for each nuclear reaction, for each fission reaction, the amount of energy that is given off to you is 50 million times larger than the reaction for coal, okay? So this has some very profound implications in the mode of operation of nuclear power plants versus coal fire or natural gas fire plants. So let's take a 1,000 megawatt power plant. That serves roughly 750,000 households. City of Boston, 1 power plant, okay? If you were to generate that electricity with coal, it will require the order of 7,000 tons of coal per day. So if you've ever driven past a coal fire plant, you see that there is a huge mountain of coal sitting outside. And usually there is also a railroad that brings in the coal on a regular basis because it requires so much fuel. Similar idea with natural gas, about 64 cubic meter of gas per second. That's an enormous amount of mass of gas that has to go through, so there is a pipeline. The implication is that this power plants are obviously subject to potential disruption, for example, if there is a weather event that takes out the pipeline or the fuel supply for coal. By contrast, the nuclear plant, 1,000 megawatt, will require order of 300 kilogram per day of natural uranium. And 300 kilogram per day is something that you can put on the corner of this thing. So City of Boston one day would consume basically this much fuel, okay? So really that, the scale is incredibly different. The implication is that nuclear power plants do not need to be continuously refueled. Essentially, you operate at full power for 1.5 years, 2 years, then you shut down for a couple of weeks, you replace the fuel, and off you go again, okay? So they tend to be a little bit more resilient to disruptive external events because the fuel is in the core and it does not need to be supplied continuously. Now, what is this magic fuel that we're talking about? Uranium is a naturally occurring element. I would say is plentiful. With a little bit of hyperbole, I would say infinite. Nothing is infinite, but close enough. So that little rectangle there represents about 100 years of uranium usage at current rate. Okay, so the current fleet of nuclear reactors everywhere in the world consumes that little rectangle. So you can now sort of walk through the different resources that are known or estimated, either in uranium-bearing minerals or things like, again, coal and other minerals that are extracted. There is a lot of uranium in the tails and so on. And you can see that it multiplies by a factor of almost 10, so 1,000 years at current rate. And then there is the real trump card. It happens to be parts per billions of uranium in seawater. And while it is a little bit more expensive to extract, it is not outrageously more expensive anymore, a factor of 2 or 3 with respect to the mined uranium. And the size of, or the amount of uranium that we have is now this gigantic rectangle that you see here. Okay, so now you're talking about tens of thousands of years of uranium worth at current rate. Right? So again, almost an inexhaustible energy source, at least for the foreseeable future. Now, where is uranium if I want to mine it, if I don't want to get it out of the seawater? It's, well, it comes from essentially 4 countries, Australia, the US, Canada, and Kazakhstan. The US has a lot of uranium resources, as you see here. However, they're not the cheapest, and so currently the US is not a big producer, but should we decide that we want more uranium, we can also get it domestically. Kazakhstan has very cheap resources, and so does Canada. Nuclear plants are dispatchable. Again, this word is important today. It means you can control the generation when you want it. They're also very reliable. They run with very high capacity factor. They can run basically 24/7 full power throughout the year. And they do not use up much land. So here I'm going to compare nuclear to solar and wind in terms of how much land do they consume per unit energy generated or capacity installed. So this is a 5,200 megawatt, 5.2 gigawatt nuclear power plant in France. This would serve a city of 4.5 million people, so a big city would be served by this one plant. It works 24/7 year-round with a capacity factor of 90%, and it sits on an area that is smaller than a square mile. Okay, so you can do the math there. That means an energy density, aerial density of almost 6,000 megawatt per square mile. Now, of course, with renewables, they have other benefits, but certainly they're not very dense, energy-wise. And so this is a large wind farm in California. Its nameplate capacity is 1,000 megawatt, and it takes up 50 square miles. And what's also important, of course, capacity factor is less than 40% because it generates only when the wind blows. So the energy density is 2 orders of magnitude down, and with solar, similar numbers, in fact, even a little bit lower because capacity factors tend to be a little bit smaller. Now, nuclear, of course, has been around for a long time, and it accounts in many important regions of the world for a majority of our carbon-free electricity now. So this is a reality. You can see here for the United States, for example, about 60% of our, again, carbon-free electricity currently comes from nuclear, and then roughly 20% from hydro and solar and wind, respectively. In China, mostly from hydro, a little bit of nuclear, a little bit of solar. In the EU, similar to the US, roughly half of their electricity, carbon-free electricity, comes from nuclear. And then there are some countries that are even more lopsided. ROK stands for Republic of Korea. I gave this talk a few weeks back in Korea, so that's why you see that data over there. So it is an important component of our power sector already in the US and other places in the world. This is sort of, this is the safety question. I'll get back to it later, but nuclear certainly does not have a very good reputation. The bad reputation that it has in terms of safety is completely undeserved. In fact, if you look at public health impact, it has the lowest of all energy sources. This is not a particularly cheerful way to look at data, but it is a rational way. It's basically the mortality rate, so it's number of casualties produced by different energy technologies per unit electricity generated, okay? And so obviously you have the big tents, the big poles in the tent are the fossil fuels, particularly when they are unscrubbed, so they give off a lot of noxious gases and particulates, and so they cause airway issues. And then at the lower end you have the more benign energy sources, and nuclear really is very low, even if you include calculated, and I emphasize calculated casualties from accidents. I'll get back to this in a moment. Now, okay, I've given you all the good news, but no technology is perfect, and nuclear certainly is not perfect. It has certain issues. The biggest problem that we're seeing now is cost, okay? So levelized cost of electricity is not the best metric to use to compare different energy sources, but it's a reasonable one. And so the table here shows levelized cost of electricity for a whole bunch of different generation technologies. At the bottom you have the non-dispatchable intermittent, such as wind and solar, and then at the top you have dispatchable, such as combined cycle natural gas, nuclear, geothermal, and others. And I would like to draw your attention to two numbers. This one here on the right, 46, this is dollars per megawatt hour, so it's levelized cost of electricity. For a conventional combined cycle, a new plant, it would be of the order of $50 per megawatt hour, okay? And if you were to generate that electricity with nuclear, it would be higher. So in the absence of a carbon constraint, the US now would essentially run entirely on natural gas as far as the power sector is concerned, okay? So nobody can compete with shale gas in the US these days. All right, on top of that, the industry has attempted in the US and Western Europe to build new nuclear power plants over the past 10 years. And these projects have gone disastrously bad. In particular, there have been a lot of cost overruns. You know, say that the initial estimate for construction of a new plant was $4 billion, and they are $8 billion. So not really good news. And schedule delays. So instead of 5 years, 10 years. And so in our study, we spent a considerable amount of time trying to understand why that happened. Because it's interesting here. You have to compare the experience in the US and Western Europe to the experience in Asia. So what is shown in this table, or in this plot here, is the overnight construction cost, which is a good measure of, well, the cost of a plant, if you wish, in different countries. And on the left here, you have projects that are led by Asian companies, Chinese, Koreans, Japanese companies, either domestically in their own countries, or in the case of the UAE, well, the UAE, United Arab Emirates. And on the right, there are projects that have been executed or are being executed in the West, either the United States or Europe. And you can see here there is roughly a factor of 2 difference in the cost. And in particular, in the West, we are twice as expensive as in Asia. So why is that? And the first impulse might be, oh, we're building different, the technologies are different. And the answer is, nope, they're the same. In fact, all these projects are large gigawatt-scale pressurized water reactors. They're all derivatives of US designs from 50 years ago. This is not, you know, is not an issue associated with I'm building something new that no one has ever tried before, okay? And so then, if you look at the real causes, and we spend an enormous amount of time interviewing folks and looking at data and looking at the way the contracts were set up, we found a list of softer issues that clearly plagued the projects in the West and clearly were absent from the projects in the East. And so you're going to laugh at some of these things because it's almost incredible. The first is, in Asia, they do not break ground on a new nuclear construction project until the design of the plant is 95% or higher done. You know, first you design, then you build. It would seem like common sense. Well, it's obviously not common sense in Europe or in the US, where we happily went to start building these plants when they were less than 50% design. And that's the recipe for disaster, because then you have to either design as you construct and make changes, and there is rework. And every time you make a change, to a major change to a design in a nuclear power plant, you need to go back to the regulator. In the US is the Nuclear Regulatory Commission, the NRC, and ask for authorization for that change. And that process, just the process of getting the authorization and having the conversations and doing the analysis and all of that, takes time, and time is money. And so the schedule starts to be diluted. Just to give you an idea, for building a new nuclear power plant, you're talking about 5,000 or 6,000 workers at a site. And if they're there sort of waiting for the regulator to make a decision, they still have to be paid, and that's a lot of money that goes down the toilet. So completion of design was a very, very big sort of flaw in the Western projects. The other thing is, in Asia, there has been a continuous program of construction of nuclear power plants for the past 30 years. In other words, these companies have not stopped building nuclear plants, whereas in Europe and in the US, there has been a hiatus of 20 to 30 years. So literally, people that were experienced and knew how to build these things 20, 30 years ago have retired, and the know-how is basically lost. This was very clear in the supply chain. Supply chain in the West was immature, so companies had a hard time cranking out components at the right quality for nuclear projects. And then integration of fabricators and constructors into the design team. You want to design something that can be built and can be fabricated and then constructed in the field. And in order to do that, you need to have the folks that ultimately will carry out that construction and fabrication as part of the design team up front. And then some other issues with contracting. So very interesting conclusions, nothing to do with the technology. There are some aggravating factors of why the projects in the West were more expensive. The first is productivity in the construction sector. What is shown here, the different curves are different sectors of the US economy, and you look at the productivity as a function of time. And the construction sector is the orange curve. And what do you see in the orange curve? It peaked in the mid-60s, so our construction sector has actually become progressively less and less productive. Now compare that to other curves you see here. My favorite is agriculture, right? I mean, if one of those farmers out there in the Midwest can feed an army these days, they become so productive. Or, more relevant to our topic here, is manufacturing. Manufacturing productivity has gone up by a factor of 8 over the past 6 years. So the implication of this is, who would you rather have build your nuclear power plant? Construction workforce or factories? The answer is obvious. You want the factories. You want the shipyards. Those are high productivity environments. Construction sites are not. The second aggravating factor is labor rates. Not much we can do there. In fact, thank God, in the US, workers are well paid. But that does make a difference on the bottom line. Okay, so we obtain labor rates for different crafts and engineering tasks in different countries. You have US, Korea, China, and France, I think. And you can see that in the case of China, of course, much, much lower than in the US, and then the other countries somewhere in between. If you take the exact same nuclear power plant and assume that the same amount of hours are required to complete a certain task, and you roll up the labor rates, you find out that with respect to China, the US would pay a premium of about $900 per kilowatt, and Korea about half of that. Now, that's a significant number. It doesn't explain the big difference that I showed you 2 slides ago, but it explains some of it, okay? So that's why I call it an aggravating factor. Okay, so, right. Then the other piece of, I guess, bad news, again, from the US point of view, is that export market for reactors that would be built elsewhere is beginning to be dominated. In fact, currently it's completely dominated by Russia and soon by China. The numbers that you're seeing here are not reactors built abroad. They are reactors that are being built in their respective countries. But this map up here on the other end shows where Russia has already inked some contracts. In any case, China been very aggressive in building nuclear power plants domestically at home, and they are very, very soon, in fact, they've already started exporting them. So for the US, in terms of geopolitical influence, that is, of course, a challenge. So our conclusion is that for the US to get back into this business, there is a need for a paradigm shift. So what do we mean by that? We compare the nuclear industry to several other important industries in the US and worldwide. So nuclear plants here compared to coal plants, offshore oil and gas, chemical plants, satellites, jet engines, pharmaceuticals, automobiles, consumer robotics, and so on. And we look at 4 categories. The first is system size. The machine or the product, is it a large system or it's a small system? And a nuclear plant is a large system. It's not the only industry. Chemical plants are large as well. Then you have things that are smaller, automobiles or consumer robotics. Testing and licensing. How long does it take to test and license a new product in this respective industry? And for nuclear, because of the safety requirements, it takes a very long time. Again, it's not the only one. If you think about satellites, jet engines, of course, even pharmaceuticals, they take a long time as well. Factory fabrication versus construction site fabrication. I already told you, for nuclear plants, traditionally is construction sites, not very productive. For many of these other products, it's factories, okay? And then lastly, what are you selling? Is a high return product or is a commodity? And nuclear traditionally sells electrons. And electrons are not painted black, red, blue, depending on who is sending them. They're all the same. So it's the ultimate commodity, all right? So if you look at this comparison, you see that in a way, nuclear is what I refer to as the perfect storm of negative attributes. The current model, the current paradigm for innovation in nuclear is like the worst you can possibly think of. Large machines, takes a long time to test and license. They do not use productive environment because it's not factory made, and they sell a commodity. Okay, so you have to turn these around. And so what that drives you to, or should drive you to, is smaller systems, more serially manufactured, again, more factories and shipyards, less construction sites, producing high added value energy products, not just electricity that is completely commoditized, and possibly with an accelerated testing and licensing. Okay, so that's how you would try to turn this thing around. Okay, so therefore enter the so-called small and micro reactors. I'm not going to get into details here, but suffices to say that the focus, particularly in the United States now, is not on the traditional large gigawatt scale reactors, but it's on smaller beasts. And this could be light water reactors like NuScale, GE, less than 300 megawatt, or a high temperature gas reactor that's X energy, less than 300, or Westinghouse is even looking at so-called microreactors, now 20 megawatt. What's the value of this? Well, the first thing is kind of obvious. Because the scale is smaller, they're not going to cost as much. Now, here is important to understand. When I say they're not going to cost as much, I mean in absolute terms. Whether the electricity that they generate is going to be competitive remains to be seen, okay? But the amount of capital that is put at risk if you build a smaller machine is obviously going to be smaller than if you build a big machine. And by an order of magnitude, it can be. So we look at the cost drivers for new nuclear power plants built in the traditional way. These acronyms here don't mean anything to you. They shouldn't, but they're just a Korean design, an American design, and a French design. And what we found is, this is the breakdown of their cost, that the direct cost of the equipment, which is shown here in dark blue and red, is only 25% of the total cost. And what really costs a lot in building new nuclear power plants is what we call yard cooling and construction or installation. So essentially is the site preparation, excavation, basement, all the reinforced concrete structures, as well as the labor that goes with it, and engineering costs and owner costs. So, and as well as financing. So the implication of this is that the innovations that you might need to reduce cost is not necessarily a new reactor design or a new direct cost of the equipment, but you want some of these other innovations. The first is kind of obvious, is standardization. You want something that is standardized because the engineering costs are dramatically lower if you don't have to re-engineer the system every time that you build a new plant. Okay, so that's the first one. We've also seen very clear economy of multiples at existing projects. If a company is building 3 or 4 units at the same site, the cost of the second, the third, and the fourth unit is a fraction of the cost of the first unit. So having people repeat the same task, they're going to become quickly better at doing it, and the costs come down. Concrete. Reinforced concrete is a big cost driver for large reactors and potentially even for smaller reactors. So anything you can do in terms of changing or reducing the amount of rebar reinforcement and the amount of material and the associated labor can really have a big cost impact, and that's a positive thing. And then modular construction and so on. So the other feature that is important about these smaller reactors is that they have a radically different safety profile. So again, this can get technical and lengthy, but the key question, technical question for safety of a nuclear reactor is, how do I maintain cooling of the core of the fuel at any given time, not just the normal operations, but also under disruptive situations. And with these new technologies, you basically have a much, much longer time before the operator has to intervene. In some cases, the operator does not have to intervene at all to maintain cooling of the reactor. And these things are done through the use of coolants that actually do not boil off, so you always have your coolant, a very large heat capacity, thermal capacity in the core, so I'm able to absorb a lot of energy without going up in temperature. It also uses engineered systems that are not active. They do not require pumps or diesel generators to drive. If you think about the Fukushima accident in Japan, it was basically an earthquake plus tsunami that disabled safety systems that were driven by pumps and emergency diesel generators. All these technologies do not have emergency diesel generators. They just work on natural circulation, pressure drops, radiative heat transfer, and they're very, very robust. So we think that the combination of these features can give you basically a system that does two things. First, very much simplified design and operations. That's really good news. The operators don't have to do nearly as much. And number two, important also, the so-called emergency planning zone, which is a region around the plant where people would have to be ready in case of a general emergency to potentially evacuate, would be shrunk down to site boundaries. So even under the worst case scenario, people would not have to evacuate. These conversations are taking place now very positively between the NRC, the regulator, and NuScale, which is one of the technologies that I showed you a couple of slides ago. And we expect within a couple of years to see the first concept here in the US to be licensed with these technologies. Last piece is this added value, okay? So how do you create value in the product that is produced by a nuclear power plant? Well, as I said, electrons are not painted or are not marked, but they could be marked if there is, of course, a price on carbon, right? So then electrons coming from a carbon-free generator would be valued higher than electrons coming from a carbon emitting. So through policy, electricity from a nuclear plant or from solar and wind could be higher value than electricity from natural gas or coal. But the other thing that is perhaps more interesting is that there are energy markets. As I said at the beginning, it's not all about electricity. A lot of the emissions are associated with other sectors, and other sectors do not necessarily require electricity. For example, industry very often requires heat. Okay, so can nuclear power plant or can nuclear reactors provide heat to industrial process? The answer is yes. What about hydrogen or synthetic fuels for transportation? The answer is yes. I'll show you a couple of examples. There are also remote islands, communities, mining operations, military bases in the middle of nowhere. Okay, so for these applications, small reactors could mean a lot. And propulsion for transoceanic commercial ships. Now, a significant fraction of emissions in the transportation sector is actually associated with shipping. Very efficient way of moving things around, but if you burn diesel or some other fossil fuel, you're emitting. District heating and water desalination. Water desalination gets a lot of attention. It's actually a fairly small market. So, in a low carbon world, in a world in which carbon is the enemy, we don't want it out there, it turns out that actually nuclear energy is going to be the lowest cost dispatchable heat source for industry. So what this table here compares is different energy sources. All of them are carbon-free except at the bottom, for reference, is natural gas at US prices. You can see immediately, if there is not a constraint on carbon, who wins? Natural gas. In the US, it's natural gas, okay? You can see the lowest cost of heat, LCOH, is gas. However, if you exclude gas, which means, again, now I have a carbon constraint, the only energy source that has low cost, dispatchable, and low carbon is nuclear, followed by solar thermal with storage, okay? So then it can become quite interesting. And if you're a factory or an industry, you want dispatchable. You don't want, intermittent. You want heat that goes all the time. So we did a site-by-site analysis of industrial sites in the United States. We used the EPA database, which essentially categorizes industrial sites according to their emissions. They have to be 25,000 tons of CO2 equivalent and higher per year. And we said, okay, if the amount of heat that is required at this sites is sufficiently high to make sense for a nuclear reactor, then you could put a nuclear reactor. Also, we look at the temperature at which this heat has to be delivered, because if the heat has to be delivered at 2,000 degrees C, nuclear cannot make it. But with high temperature gas reactor around 650 degrees C, that's feasible. And so when you look at this, the bottom line is really shown in the little box here. We found that about 20% of the industrial heat in the US could actually come from nuclear. And that's an equivalent capacity of 150 gigawatt of heat load, which is significant. It's about half of the current fleet of nuclear reactors. So it would be a significant growth opportunity for the nuclear industry and would account for about 7% of the total US greenhouse gas emissions in the US. So again, that's accessible now with essentially no fancy new technology. The real game changer outside the power sector is transportation. Okay, so the numbers that are shown here are for US, France, Japan, and the world overall, and they assume that the entire fleet of cars and light trucks are replaced with either electric vehicles, that's the first column, or fuel cell vehicles, that's the other column. And so in the US alone, if we were to replace if we were to replace all our, I don't know how to go back, but okay, doesn't matter. What is it? Maybe. No, they aren't going the wrong direction. Never mind. Let me just say it anyway. 250 gigawatt of new electricity would be required if you were to electrify the whole transportation sector in the United States. Okay, so current fleet of nuclear is about 100 gigawatts. So that would be, again, tripling. I mean, of course, it's not realistic to assume that all that new capacity would be nuclear, but a big piece of it could be. So again, potential growth is there, but it requires a clear policy that says, I don't like carbon. Okay, I think this is consistent with what Dan was saying for a different application. In the absence of carbon, nowadays, fossil fuels, particularly natural gas in the US, dominate. Okay. All right, so policy options. How many time? 5 minutes? 6 minutes, okay, perfect, plus a couple of questions. Policy options for the US. So our study clearly makes the point that the current fleet of reactors, we have about 100 reactors in the US corresponding to 100 gigawatt of electricity, should be preserved. Why is that? The first point that we make is that if in the future it turns out that the US says, okay, I'm going to need more nuclear, you want to retain the technical expertise to operate these plants. Now, the plants are currently operated at an exceptionally high level of efficiency, 92% capacity factor. That's absolutely mind-boggling, stellar. But it didn't happen overnight. And what this plot is showing is the behavior of the capacity factor over the past 30 or 40 years. And so when the current fleet was actually built 30, 40 years ago in the US, the industry was not proficient at operating these plants almost at all, and the capacity factor was less than 50%, now 92%. Okay, so that technical expertise has to be retained. And the same thing goes for, in efficiency and safety in operations. This is the number of, this is the rate of safety accident rates per 200,000 worker hours. Has come down very, very dramatically, much lower than the goal, and order of magnitude, by the way, than the general US industry. Okay, these are accidents on the workplace. So again, you probably want to keep it there. The other reason for preserving the existing fleet is that every time a nuclear power plant shuts down, the emissions go up. And this is not speculation. We have a couple of examples already showed that a nuclear power plant is shut down, the CO2 emissions in that state will increase, okay? Even if that capacity is replaced by solar and wind, because with solar and wind come the backup typically, which is natural gas, and so you get emissions out. Our calculations show that, in fact, keeping the current nuclear power plant is the lowest cost form of constraining carbon emissions. So it's a very easy calculation to do. You say, okay, let's suppose that you shut down the nuclear power plant, replace it with an equivalent capacity of solar, wind, plus natural gas that will preserve the amount of emissions that you get out, and that's a certain cost, versus what is it going to take for this plant to stay profitable. That's like a subsidy. And it turns out that between $12 and $17 per megawatt hour given to a nuclear power plant will make it profitable, and that's about 3 to 4 times less than what you would spend to replace that capacity with other generations. So it's actually a good deal, assuming, once again, that you care about emissions. If you don't care about emissions, shut them down, put some new natural gas only, forget about solar and wind, everybody's happy. But that's, I don't think, what this crowd feels. Some states have done exactly that, what I described, the positive thing. They've given zero emission credits to nuclear plants, New York, Illinois, New Jersey. It's of the order of $12 to $17 per megawatt hour. Very interestingly, this approach has been endorsed also by some historically nuclear skeptical organizations. The Union of Concerned Scientists, Conservation Law Foundation have come out publicly saying we must absolutely preserve the nuclear power plants, because if we shut them down, it's going to be a big setback for the environment. There are some other policies that the government could implement to spur private investment in new nuclear. What we have now in the US is state by state, sort of a patchwork of policies or subsidies or supports. Some are like renewable energy standards or portfolios. We advocate for putting all low carbon energy technologies on the same level. So replace renewable with clean, and that includes also, nuclear or even fossil fuels if you do carbon capture and sequestration. So if the goal is decarbonization, then we shouldn't sort of pick 1 or 2 technologies. We should have all the technologies that can get you to the target to be part of that. It's also the government's responsibility to find I stress out, politically durable solution for the spent fuel disposal. It has never been a technical problem. It's always been a political process problem. I can get into that if you have an interest. And finally, the government should spend money on R&D that makes sense to reduce cost and make this technology again viable. I would say there is hope. I want to leave you with a positive message. There is very, very robust interest in new reactor technologies, the kind that I described earlier, with, for the first time in decades, support from private, from the private, sector or private capital. Traditionally, nuclear in the U.S. has been very much a government-driven operation, if you wish, in terms of developing new reactors and so on. Now there is private capital invested in these new technologies. Some very influential advocates like Bill Gates, he actually is the primary investor in a company called TerraPower, which has been in existence for 10 years, based in Seattle, developing one advanced reactor technology over there. And the last slide here is, again, a little US-centered. The rest of the world is rushing ahead of us, in particular China and Russia. China in particular on nuclear is the de facto leader when it comes to advanced reactor technologies, but the US is capable of catching up very quickly. Now, this is a fantastic project that NASA actually put together for a small reactor. In their case, they're not concerned about powering the grid, but they're concerned about a power source for deep space missions or even permanent bases on the moon, Mars, and so on. And they were able to design, fabricate, and test a small nuclear reactor for less than 3 years and less than $20 million, which is really peanuts. So, I mean, in nuclear world, when you think about a new reactor technology, you're usually thinking 20 years and $10 billion. And here, NASA was able to do it in a very short period of time and literally on a dime. And it worked like a charm. So if NASA can do it, the industry can do it, the Department of Energy should be able to do it. NASA is a very good agency, though. So with that, I'm not going to repeat the takeaway messages. You see them here. Selfish plug-in. The report or the study that I've been mentioning all along has produced a report which was issued back in September, and you can freely download it there. And with that, I'm almost perfectly on the spot, and I can take a few questions if Jules kindly allows it.
Yeah, so in the interest of time, let's just take 2 questions, quick ones. One from here, if there's any. Yes. So that's natural uranium, that's not fissile uranium. So we have to.
Yeah, so first let me repeat. The question is, I think you're asking about the math of having 50 million units more of energy. How does that become 300 kilograms as opposed to, say, 7,000 tons of coal? Yeah, well, first of all, there is this stoichiometry that, an atom of uranium is heavier than coal, so that comes into play. But the other thing is, as Jules said, is I gave you the 300 kilograms, that's natural uranium. If I did only uranium-235, which is the actual isotope that is fission, it would be 3 kilograms. So then the whole city of Boston would be basically fueled by something that I can hold in my hand in one day, 3 kilograms, okay? And that's how much energy there is in this material. It's incredible, really.
Okay.
Yes?
Yeah, there's one.
Hi, over here.
Yeah.
Can you see me? I have no expertise here, so feel free to tell me if I'm wrong. But my understanding on the point of dispatchability is that many current nuclear plants are actually designed sort of as baseload plants, and maybe for safety reasons and other reasons, they don't actually ramp up and down very often. So I was wondering, this next generation, these sort of 3 types you're talking about, how will they differ on that front to allow for the dispatchability that you're talking about?
Yeah, that's a great question. So you are right. The current fleet was designed to be base load, but in fact, a large fraction of our nuclear power plants now, the existing fleet, is already following the load, and quite aggressively. It has to, particularly in deregulated markets, and particularly in markets that already have a high penetration of renewables. For example, the Midwest, there is a lot of wind, And so the nuclear power plants are actually already following the load. And they can do that with a, I would say, an efficiency that nobody had suspected just a few years ago. In Europe, in particular in France, which has a very large fleet, 75% of their electricity is nuclear. Some units have always done load following because they had, in a way, an extra capacity of nuclear and they had to adapt. But to the second part of your question, all the new technologies that I show there are designed from the beginning for doing full load following. I think that's the reality of the grid is such that base load, traditional style is out and you have to be able to sort of accommodate. It's never a winning proposition from an economic point of view because these are high capital assets. You'd like theoretically to run them always at 100% power, but the fact is that if you want to be a good citizen of the grid, you have to be able to follow load.
Yeah. Okay, let's thank all the 4 plenary speakers in the morning for very exciting contributions.